Okay, so we're going to continue with chapter 4, and we were looking at how we pipeline the processor and how it is an easy and natural evolution from the single cycle implementation. So it's a good idea to go back and just take a look at the full single cycle implementation with the control, because we had already decomposed the data path for the pipeline implementation. We have added the pipeline registers, and we were about to add the control. And since, again, as I mentioned before, the pipeline implementation gives you the best of both worlds. It's simple control that you can send down the pipeline, but also you get the speed improvement that theoretically can approximate an improvement fold that is as many times as pipelines stages you have. So this is the single cycle data path with control. Very important for you all, because your next lab is going to be doing just this in Verilog. And this is the pipeline data path that we had with the pipeline registers. And we had put the control signals for data steering, for the muxes, and for the reader writing of the memory and the register file, and also for the branch flag. So the question is, how do we add control? Well, it's actually the same control that we had for the single cycle, and we're going to determine those control signals during the instruction decode stage, which is this stage here that comes after the instruction fetch stage, which is this one. We also are going to use the same ALU control that we had been using, and that is going to be in the execution stage. So we still, this logic is the same one that we had formulated with the same truth table that we had come up with for the single cycle. But now these control signals are going to be generated in this stage from the main control, which is the same as the single cycle, but the control signals are going to travel down the pipeline through the pipeline registers to reach the stage that they need to reach when they need to reach it. So it's going to be synchronized with the instruction. So again, this is the truth table for the ALU control. We already saw that, and these 2 bits are coming from the main controller, and in the pipeline version are going to come through the pipeline register, and this is going to come from the instruction itself, which also is going to travel down the pipeline register. And together we are going to be able to determine what the ALU function is, which is determined by these outputs. So these are the outputs of that logic, and the opcode field and the ALU op bits are the inputs. These bits depend on the group of instructions that we have, and this one depend on the actual instruction. This is the same truth table that we had for the main controller. So here we're going to be generating, these are data steering signals for the instruction decode stage. These are the ones that go to the execution stage. This one goes to the memory stage, and this one goes to the write back stage, the last stage. But it's the same logic. They're both combinational logic blocks or truth tables. So here we generated in the instruction decode stage and we just add width to that pipeline register, and we send them down. So the next stage here is the execution stage. So that's where the execution signals go to, and they die there. They're not used beyond that, so we don't need to keep sending them. We just need to send the write back and the memory stage signals. And here in the memory stage, these ones get used, and that's where they end. And then we only send down the write back signals and so on. So that's the concept of control implementation for pipeline. It's very simple. It looks just like the single cycle. We just need to make sure that we synchronize them through the pipeline registers. So here's a depiction of the pipeline data path with the control, with the signals routed through the pipeline registers. And again, we know what the truth table is for this. We've seen that, and we know what the truth table is for this. Now let's go back and revisit hazards, because we said that we can solve via forwarding any type of data hazard if we have the data in the data path or in the pipeline stages somewhere. But we haven't done anything to make that happen yet. So now we're going to look at that, and the easiest thing to do is to consider a sequence so we can illustrate, and it makes more sense what we're going to end up doing from a hardware perspective. So let's consider this sequence. Here we have a subtraction instruction, and the destination register is register 2, which is used as a source in the very next instruction by another register or arithmetic logic instruction. So we know that we're going to have a data hazard here, and we're also going to have one here. And we keep using that register. At some point, we're not going to have a hazard anymore, but we keep using that register as a source for the next few instructions after it is declared as a destination in this first instruction. So the question is, how do we detect when to forward, from where to forward to where, and what is the logic conditions so we can formulate Boolean equations that we can cast into hardware? So to do that, as an example, let's look at this sequence. And we're going to be utilizing our pipeline diagram, simplified diagram that we discussed last time. So here we have we're fetching the subtract instruction here. Here we are reading register 1 and 3. Here we're doing the actual subtraction. Here we're not doing anything. And here we are writing register 2. The next instruction we are fetching here. Here we want to read registers 2 and 5, but register 2, which is the result of the previous instruction, at this time is right here. It's right here at the output of the ALU. So what is going to come out of the register file is not the right result. It's the old value of register 2 that we're going to overwrite 2 clock cycles later. So what we need to do is, we don't want the output of the register file that is shown in here to go into the ALU in the next stage or in the next clock cycle. What we want is what came out of the ALU in the previous clock cycle. So this red line here, that's what is signaling a forward. We are forwarding from the execution stage of the previous clock cycle to this clock cycle execution stage that value, because that's what it is. We cannot take it from the register file because that is a stale value. So now we do that. So we grab the right value of register 2 and we do the ANDing operation here. At that time, we are trying to, or we're fetching the OR instruction. And here we are reading registers 216. But the right value of register 2, the right value of register 2 now is over here. So for the execute stage of the OR instruction, we forward it from the output of the next pipeline register. At this point, we still have not gotten the right value into the register file for it. So we have to forward from the stage, the memory stage, as it goes through the write back stage to the execution stage of this instruction. So that would be from 2 clock cycles later, before. And we have to keep up with which port of the ALU we need to forward to. Notice that here, it was the first source, so it goes into this port. Here is in the second source, so it goes in the second port of the ALU. Now, in this clock cycle over here, we're fetching this instruction. Here, we are fetching or reading both registers from the register file to be register 2. So both outputs of the read ports are going to be the same register, register 2. But we haven't finished executing that stage. Okay? But by the end of the cycle, we are going to have the right values. And when we go into the next clock cycle for the execution of this add instruction, we are going to have the right values of, or the right value of register 2. That is only if the register file is architected in such a way that when I'm writing, the data that I'm writing, if I'm reading at the same time, that same register, it goes through to the output read ports, which is easy enough to do. Okay? And then here again, we are fetching this instruction, the store, and register 2 is a source register. So we can definitely, when we read that register, it is the one in the register file. So there are no problems and no need for forwarding at that point. So hopefully that gives you an appreciation for the complexities of what we mean by forwarding and how we can methodically look at the different conditions and situations and formulate logical Boolean conditions under which we have to forward from where to where. So that's what we're going to look at next. So the first thing that we need to do is we realize that we need to pass the register numbers that are involved in the instruction. We have to pass those along the pipeline. And you can see now our pipeline register is growing because we just add more bits as we need to pass them along. Uh, and also, we need to detect them. And then we have these conditions by looking at the dependencies of the register fields that are present in the different stages. So when we have the RD field, destination field, in the execution to memory pipeline register equal to the source 1 in the instruction decode execution boundary pipeline register, when those two fields are equal, we need to forward from the execution stage to the ALU. Same when the destination is equal to the second source register. Also, when the destination in the memory write-back boundary register is equal to the source 1 in the instruction decode execution boundary register, we need to forward from the memory write-back boundary pipeline register. We need to forward those results from there. And also when the destination in this boundary register, memory write-back, is equal to the instruction decode execution boundary register source, second source, we also need to forward from the memory write-back boundary register. So if we go back to the previous slide, the first two conditions, 1A and 1B, are this type of forwarding. Is this type of forwarding. Which one we go into, this port of the ALU or this second port, that's your 1A versus 1B condition. So the specific line that we have here corresponds to 1A. And this one is your 2, your second set of conditions. In which one we go into the first port of the ALU or the second port is your 2A versus 2B. So this specific red line corresponds to 2B. So that gives you these 4 conditions. So we're going to simply generate logic to detect these conditions. So the other thing to realize is that we only need to forward if we're going to write to a register eventually. So we have to watch for the register write control signal, because there are instructions that don't write to the register, such as the branches. And if the destination register is the 0 register, then the 0 register is a read-only register. It never gets written. So we can ignore the condition if the RD field is equal to 31, which is the 0 register. So these are some additional details to detect. So again, we're going to be passing these register number fields to through the pipeline registers. And the unit that is going to do these comparisons and generate the data steering that, as you know, is always done through multiplexers, we're just going to call it a forwarding unit. Okay? So as you can see, this forwarding unit takes as inputs the source registers from the ID execution boundary register and takes the destination from the execution memory boundary register and from the memory write back boundary register. Those are the inputs that we need to see if we need to forward. And where do we need to forward from? So if we go back, you can see that we're using the original source register. So these two over here, that's this two. And then the ones on the left-hand side, this one is the other input, and this one is the other input. So this one is condition 1, and this one is for condition 2. And for each one of this, looking at this two gives you the 1A, 1B. So 1A is comparing this one with one of this. 1B is comparing this one with the other. 2A is comparing this one with one of this. 2B is comparing this one with the other one. So according to that, we can come up with the forwarding. And the forwarding is going to be generating as outputs for data steering. So these are the outputs. Remember that comparators are combinational logic. So this is just a bunch of combinational logic. And given that combinational logic output, we generate the forwarding signals. So here we have expanded the muxes in front of the ALU to be able to forward. If we are not forwarding, so this, you can see that this is a 3-to-1 mux, so these lines are 2 bits each, because you need 2 bits to select from 3. If we are not forwarding, then the path is the normal path that we had before. Okay? If we have to forward, let's just call this output forward A. If we are to forward for A, we have two possible conditions. We can forward from the write back stage. So we have here from the write back stage. So we forward this way. Or we can forward from the memory stage here. And that is if we forward into the first port of the ALU. So this path is your 1A, this path is your 2A. And then for port B, we can also forward from the write back or from the execution memory stage. So let's go back to make sure. So the second condition is from the write back. So actually this is 2A and 1A over here, and this is 2A, 2B and 1B. So here we're forwarding from the write back into the B input of the ALU, and here we are forwarding from the execution memory into the B input of the ALU. So 2B and 1B, 1A and 2A. So now it should make a lot of sense for you that by looking at these fields and comparing them, what we're doing is detecting if we have a dependency that creates a hazard, and we are computing, in a sense, the need to forward and affecting that forwarding via data steering through controlling these muxes. So this is a truth table, which does exactly what I just went through. Okay, this would be the possible values of the forward A signal. So here we have the regular no forwarding, okay, and here we're forwarding into the A input of the ALU from the execution memory boundary register, and for input B of the ALU, here we have no forwarding from the execution memory boundary register, and here forwarding from the memory write back boundary pipeline register. Now, let's consider if we have a double data hazard, such as this. We are using register 1 as a destination register, and then we use it as a source. So we know that that gives us a hazard, but now the destination is also register 1. Now we have another hazard here, followed by another hazard, because now register 1 is being used again as a source. So in this case, you can see that there is no need for this result to ever make it to the register file, because it's going to get overwritten anyways by another operation that uses it. So we want to be able to pick up the most recent one. So let's just revise the hazard condition for the memory stage, and only forward if the execution stage hazard condition isn't true. Okay? Because if we have a hazard coming from the execution stage at this point, then we know that it's going to get overwritten anyway, so we can clobber that value. So here's our revised conditions. And notice how this is almost looking like pseudocode that I'm able to cast in something like Verilog or VHDL to generate my outputs, which are my forward A, forward B control signals. So I can say if I'm going to write a register, And the memory, the register is not 31 because 31 doesn't get written. And this condition is not true. This ending with this. So this is basically what we have here. And these two fields are not the same. And these two are the same. Then I'm going to forward into port A of the ALU. And this would be, according to our table before, we're going to forward from the memory write back boundary pipeline register. And then the second revision has to do with exactly the same with looking at the register write signal, looking at that we have a register that is not the 0 register, and then this condition. And if we don't have this logical condition, which is we don't have the register write, and the register is not 31, and we don't have this equality, and we do have this equality of the destination with the second source register, then we're going to forward into B from the memory unit. So notice that this only affects the memory, forwarding from the memory unit. So this is just a revision to that condition for the memory unit. So now we're going to forward into port B of the ALU from the memory unit. So we have revised that condition. So here's where the forwarding unit sits. We're looking as before at the register fields from the memory stage, from the write back stage, and from the source fields from the execution stage, but also we are looking at the write back signal now, both from the write back stage and also from the execution stage to make a determination. So these extra conditions that we put in, what they add are these two control signals for the register. I mean, these two control signals into the forwarding unit. So we have been evolving our design in that manner. So let's look at that sequence and see exactly what happens. So when we have the first instruction moving through the memory stage, we can detect that these two are the same sources. The sources here and the destination here are the same. So X1 is coming into here. And this one is also X1 at M. That's the first destination. So now we see that those two are the same, and we can generate the write control. So this is X1 over here, which goes there. X1 is also, the value of X1 is here. But that's not what we want. What we want is here. We want this one, not this one. So we made the comparison. And by controlling the mocks and generating the right forward A signal, we block this and get this X1 over here. So hopefully this gives you a good view of the mechanisms and the techniques employed for detecting hazards and detecting and affecting forwarding. So you have to really look at the different conditions throughout the pipeline, where things are, where the items are, how you get to them, and specific conditions that make that the right thing to do. But we have done that for the simple pipeline, but the procedure, the thought process is the same. It can just get more complex if, let's say, you had an 11-stage pipeline, because you have to consider all the possible cases, and that grows as the number of stages in the pipeline grows. So let's do an example for this code sequence. The first instruction is a subtraction of register 3 from register 1, with the result going into register 2. So here we are, we fetch the instruction here, this one here. Now it's in the instruction decode stage. So you can see the number of the registers, they're going down. Now the pipeline register. And now we are fetching this, which is introducing a hazard because the destination here is the same as the source in the very next instruction. So no problem for this instruction. We're just going to take the values of register 1 and register 3 and do the operation. Now, when we are going to execute this AND operation, we don't want what is going to come from the register file. We want this, which is now over here, and it's going to go to the output of that pipeline register after the next clock cycle. So here we are. So we detect the hazard and forward that value to the ALU to execute this instruction with the right value of register 2. Here's this instruction that is coming down the pipeline, which introduces another hazard. In that case, the value that we want is over here, or over here. Doesn't really matter, because the mux is combinational, so it's part of the same block. So we are forwarding it now via this path to execute this instruction. And it's also being written into the register file. And because of that, we do grab the right value of register 2 for this instruction over here. But register 4 over here from this instruction did introduce a hash to this instruction because register 4 is being used over here. So now it has to be forwarded into the ALU. So in essence, for this specific pipeline, when the hazard is introduced by an instruction that is immediately following another one, you forward from here. If it's separated by one instruction, you forward from here. If it's separated by 2 instructions or more, then there is no hazard. And that is a function of the number of stages of the pipeline and where the resources are located in the pipeline. And there you have it. All right, so now let's consider the case where we have a load. Now we always say that if we have something inside the processor, we can always get it to where we need to, we can forward, but the load, we don't have necessarily the item in the processor, is in memory. We are loading from memory. And because of the nature and the structure of our pipeline, what we're going to see is that there is going to be one clock cycle where we are not going to be able to forward because we still don't have the data. So we're going to have to introduce what we call a stall cycle. It's equivalent to a no-op or a null operation or a no operation. Is essentially a clock cycle that nothing is happening for one clock cycle for each of the subsequent stages of the pipeline to give time until we get the data from memory, and then at that point we'll be able to forward. So we don't need to stall for all the clock cycles until that data is in the register file. We don't need to do that. We just need to stall enough until we get it from memory into the processor, and at that point we can forward. So we're going to be using both techniques. We're going to minimize the stall, which is going to be only one clock cycle, and then we're going to forward. So what are the conditions for this? So we have to check for that load use hazard when the memory read instruction is asserted, and if the destination of the instruction decode execute boundary pipeline register is equal to either of the source registers. Okay? So if we detect that, we know we have a load, and we need to introduce a stall. Now, the stall is part of our control. So even though we had this forwarding unit here, we're going to put that stall detection over here because stalling the pipeline downstream is part of our control mechanism. So we're going to have to augment our control mechanism with those control or stall control signals, which is really setting the control to 0 or deasserting them. So that's why I make a lot of emphasis in the importance of understanding that signals and actions take place when the signal is asserted. And you have to determine what your assertion level is. So it's easy enough to say, if it's 0, that signal is not active. If it's 1, it's asserted. So in a sense, I can have the control here, just if we have to introduce a stall, just 0 out the control that goes downstream and implement that as a no op or no execution control. And that's what we're talking about doing here. One of the big things that the control and the stall has to do is to prevent the program counter from updating, from being updated. So we have to inhibit. And that's why I also make a lot of emphasis on using enabled registers. So you have that cycle-to-cycle control of writing the registers, and they are not just registers that are free-running at the mercy of the clock, because the clock is always going to be running and providing edges to update registers, but you don't want to do that on every cycle. And you don't want to gate the clock either. That's a bad design practice. So using enabled registers is very important. So we're going to prevent the PC from being updated so we don't get a new instruction, because we have to wait. In essence, another way of looking at it is that you are fetching the same instruction again. And that has the same effect of waiting one clock cycle for the data to get into the processor and you being able to forward it. So here's what's happening. So we are, in essence, stalling the pipeline. So notice that here we are doing the load. We detect that is a load and we have to stall. So this AND, the second instruction, AND, becomes a no operation. So here we fetch the AND, but by inhibiting the control down the pipeline and at the same time inhibiting the processor, the program counter from being updated, the same AND that we fetch here, we fetch it again in the next clock cycle. And we start executing it again. We restart that instruction. So in essence, we have introduced a dead clock cycle, which is sometimes we call it a bubble, a stall, but that's the effect. By doing that, it allowed this stage to execute the memory read and get the data inside the processor over here so we can forward it now, because we are loading into register 2 and we're using it as a source. Now we can forward here. And in the next cycle, then we write, and then we're fine. And then if we use it, like in this, no, there is no hazard here, but just wanted to illustrate the stall and the forwarding for the load. That's all. So now we have to put this what we're going to call a hazard detection unit, although this is also the, detecting hazards as well. But from a naming perspective, we're just naming this forwarding unit, and we're just naming this hazard detection unit. So we're going to be looking at the write field from the instruction and the destination from this stage, and that gives us if this destination is equal to either of the sources from this stage, meaning that, and also if I have a load, right? We have to look if I have a load instruction as part of this inputs here. Then I know that I have a load followed by another instruction that is requiring that destination as a source separated by one clock cycle, and I have to introduce a stall. So here's the output, and that allows me to pass the normal control or zero out the control through these mocks. That's what this is saying over here. The other signal that I'm looking at is the memory read. That's really what tells me that is a load as well. So it's not really, it's not the opcode from here. These are just the sources, the source fields for the registers. This is what tells me that is a load because I'm reading the memory. This output here inhibits this pipeline stage from being updated. That, along with inhibiting the PC, the program counter from being written, in essence, allows me to refetch the same instruction. So together, by fetching the instruction that came after the load again and zeroing out the control, I'm affecting that stall for one clock cycle, which is what I need to get the data from memory into here at this point. At that point, the normal forwarding mechanism takes over, and I'm able to forward from this stage, from the output of the memory right back pipeline stage boundary. So with that, and as far as this pipeline is concerned, we are able to deal with all the cases of data hazards that we can have. So let's look at that with a code sequence like we did before. So here we have a load into register 2, and now we are using register 2 as a source. Destination register 4, and here we have a double data hazard on register 4. But these are arithmetic units. So, and we also have so these are just data hazards. So let's look at this sequence from the perspective of forwarding, stalling detection, or load detection, and producing the stall. So these are the types of hazards that we have here. So we fetch the load, and here we're going to start our hazard detection. So here we are, the load is over here. So at that point, the memory read instruction is 1 because we're going to be reading the memory in the next stage. We have generated that, and it's with this corresponding instruction. So now that signal is 1. Also, the destination, so X2, the address for register 2 is here. So we are going to compare that, and we see that this instruction over here, which is sitting over here, has the sources of 2 and 5. So if this one is equal to one of those, I have to stall. And the other condition is, and if memory read is 1, meaning that this instruction is a load. So if I have a load here, and the destination of this stage for the load is equal to any of the sources for this next instruction, then I need to stall. So then I'm going to stall. I'm going to select the output so I get the zeros in there for the next stages. And I also fetch the AND again. So here the AND stayed in this stage because I'm not advancing the pipeline. Now, at the end of this stage, I have the data that I need here for the AND instruction that stayed in this stage, held back, because I refreshed it again and I didn't update this register. So nothing is happening here. Now we are forwarding from this stage through this mechanism that we already went through. So we are essentially forwarding into port A of the ALU to the value of register 2 over here. And we just keep detecting data hazards with just this forwarding unit that's before. So this example actually is cumbersome in the sense that it didn't need to go into all the extra data hazard detection because we already seen that. The point was just to show the load, the generation of the stall, and the ability to forward from the memory write back boundary register back into the ALU. But these ones are just data hazards that we know how to handle already. So they're just going to go through that. I'm not going to really go too much into that. It becomes tedious and cumbersome. So hopefully you get a good appreciation of the things that are involved in dealing with data hazards and how to generate stall cycles in a pipelined CPU. And of course that every time you stall, that's a cycle where nothing is happening. So that's going to degrade your performance. So you want to minimize that. And sometimes you can, but the idea is that you want to minimize that. One way to do that and to help with that is by the compiler rearranging code so that you essentially rearrange instructions to insert an instruction with no dependency into what otherwise would have been a stall cycle. So now you're using that And now you're using that, and that's sometimes called a delay slot. And if the compiler knows and has that knowledge about the structure of the pipeline, then the compiler can do that, and it's very useful. Now let's keep talking about branch hazard, which was our third type of hazard, and as I mentioned before, the most complex to deal with because it deals with flow control. Let's look at this code sequence. And here I have a branch on 0 that gets fetched during this clock cycle. Here we are reading register 1, and here we detect if we have the condition that passes through, and here's where we update the PC. So we are supposed to branch over here. Here's where we update the PC. And we're going to be fetching from this address, the branch target address. At that point, I have 3 instructions already in the pipeline. Okay? I have 3 instructions. So we have this one at the register or instruction decode stage. This one is being executed, the OR instruction, and the AND is already in the memory stage, just bypassing the memory, right, to write the register file in the very next cycle. Well, luckily, we never get to actually write anything to the register file, so that actually makes it, that's a good thing. It's a reason to have the write at the end of the pipeline to make sure that we don't have to rewind anything that we have written to the register file, which represents the state of the machine as far as the programmer is concerned. So that would be more complicated to do. And in general, that's what happens, that because the writing of the register is delayed to the end of the pipeline, you don't have to worry about rewinding that. And it's okay for longer pipelines, so it just works out. And if you have a very short pipeline, which is not really realistic, then you may have to worry about having written the register file with things that you don't want to. But that's not the case here. But we still need to inhibit the completion of these instructions. We need to essentially make sure that these instructions, that this doesn't write ever register 12, that this doesn't write register 13, and this instruction doesn't write register 14. So we have to flush the pipeline. That's the term that is used. We have to flush this instruction, these 3 instructions, from the pipeline to really make it so that after this instruction, what came was this one. That is if the branch is taken. And clearly you can see that we wasted 3 clock cycles. So a branch taken condition cost us 3 clock cycles. And we're going to talk about how to minimize that by branch prediction. If we guessed, I guess if the branch is not taken, then there is no harm. We're talking about when the branch is taken, that we end up, in this case, giving up the 3 clock cycles, and we have to flush the pipeline, which is just making sure that after we know that the branch is taken, we intercept the control lines and set the control to 0. Now, one thing that we could do is to find out sooner if the branch is taken or not. Now, to do that, what we would do is move the hardware to determine the outcome of the branch from the execution stage to the instruction decode stage. And what that's going to require is that we have an adder to compute the target address, and also that we have a comparator for the register to see if it's 0. Okay? So in this case, for example, we could, if we move that, we can find out if this branch is taken. Okay? So this is what we've done in this new diagram. We have put the branch target computation here. Is essentially the shift by, if you recall, the shift by 2 to convert the address from word to bytes, and then add that with the value that comes from the pipeline register, the previous program counter, and that becomes the new program counter. So this is the branch address calculation. And this over here compares the register to 0. So if we go back to the previous slide, this is going to compare the value of the register to 0. And that's enough information for us to find out if the branch is going to be taken, and now we don't have those 3 cycles of penalty. Okay? So here we have a subtraction, and here we're fetching the branch instruction. At this point, we detect that the branch is going to be taken. We have calculated the new branch target address, and the control can activate a flush signal for this pipeline register here. It's the same as, it's not going to be enabled, essentially. It's not going to let the instruction advance, because that instruction was fetched with the previous program counter, which is not the right one, because that program counter was for the very next instruction, not for the branch target address. So in essence, this mechanism has the same effect as introducing one stall cycle, and there is nothing we can do about that, but we have reduced the penalty for branch taken from 3 clock cycles to 1. From 3 wasted clock cycles to 1 stall. So it does have the same effect as stalling the pipeline, but only by 1 clock cycle. Now we have the right instruction. So that was pretty easy to do in our short pipeline, but dealing with control hazard becomes a major challenge as you have deeper pipelines, as we'll see, where you have multiple replicated pipelines in what is called superscalar processors. Because now you have a huge number of instructions potentially running in the processor at the same time. Not only you have more stages of the pipeline, but now you have pipelines in parallel. You have multiple pipelines, which is the superscalar approach. So you have to, being wrong on your branch prediction can have huge implications of cycles that you are not using. And you have to flush a lot of instructions from the different stages and different pipelines. So what we want to do is get very sophisticated and talk about dynamic prediction, in which we, as I mentioned and introduced before, we're looking at the actual trend of the outcomes of the pipeline, the outcomes of the branch, and make a prediction whether it's taking or not to minimize the chances of being wrong and having to stall the pipeline and flush the pipeline. The elements of that are going to be things like a branch prediction buffer, where we store this history of branch behavior. And also we can store the branch target. So branch target buffers, we can use that. And we'll see how we do that in the next time. Next time we're going to start discussing that.